The volume is off.
Okay, sorry. Is that better?
Yes.
And let me put the. Could you guys see the slides? All right, you should be able to see the urinary system.
We can see the slides now.
Okay. Yeah, I'm not gonna. I was saying I'm not gonna. You know, it's the last lecture. I'm not gonna go deep into this. I'm going to talk a little bit, just introduce the urinary system. I'm not going to go into it, but it's actually a really important. It's a really important lecture that I should have. I'm not. Just saying it's important for you to know. So at least I should introduce you to it, because you will have urinary stuff in the future. So if you look at, so here's the aorta, right? It's the heart. It arches up here, and then it descends down here, and then here it is. And then you can't really see it, but you know there's a branch, you know, a renal artery that goes into each kidney, and then there's a renal vein coming out of each kidney. And that one you can definitely see, and that's going back up to the heart. So the kidneys are, well, the kidneys have a few jobs, and actually their main job is not really filtering blood. I mean, that is one of their main jobs, but I would put first as regulating electrolytes. So like sodium, potassium, calcium. We've talked about those this semester. Regulating those, regulating the amount of protons, like H pluses and bicarbonate. That's probably the first function of the kidney. And then a close second is removing waste from the blood. You know, so when it removes waste from the blood, here you can see the ureter going down into the bladder. I always point to the ovary. The ureter going down into the bladder. So make the urine, put it into the tube, down to the bladder, and there's the urethra, and then out. So not too complicated of a process. There's the adrenal glands on top. We're not going to talk about those. That's it. That's your urinary system. It's your kidneys, ureter, bladder, urethra. And so there we go with the function of the kidneys. You should at least know the function of the kidneys, right? So regulating electrolytes. Here I'm writing regulate blood ion composition. Blood ions, they're electrolytes. Electrolytes are minerals, like they're minerals, like we classify minerals as two types, major minerals or trace minerals. And the only difference between that is which ones do you need more often. For example, iron is a trace mineral. You don't need it as often as sodium. It doesn't have anything to do with importance. So I put a few there as an example. Sodium, potassium, that's the K+, calcium, chlorine. There's other ones. So I actually did put that as first. And then second, regulating the pH of blood. Regulating the acidity of blood. Blood has a pH of about 7.4. The pH of blood cannot move too much on either side of that. So 7.35, 7.45, that's about it. So your kidneys have to keep that pH right around 7.4. And what it will do is you see two things here, excreting and conserving H plus protons, and then HCO3, whatever negative, that's bicarbonate. So protons, bicarbonate. Protons make things acidic. We call them protons because, hydrogens, all hydrogens are protons and electrons, actually. Hydrogens don't have any neutrons. So that's all hydrogens are, protons and electrons. And if they lose their electron, which they did, that's why it's a plus, because they lost an electron. They lose their electron, we just call them protons, because that's all that they are now. But anyway, protons make things more acidic. Protons are hydrogen ions. And then this other one, this is different in that it's a bunch of atoms, right? It's hydrogen, carbon, oxygen, 3 oxygens. So we call that bicarbonate, and we consider that an electrolyte, even though it's not a mineral. It's not something like on its own. But anyway, bicarbonate makes things basic or alkaline, and protons make things acidic. So your kidneys can influence how much bicarbonate or how much protons are in your body. You've got 2 places you can do this. One's through your kidneys, and then the other is by breathing out. When you breathe out carbon dioxide. So there's your body has 2 ways of regulating pH. But this is kind of the main way. And then blood volume, right? We know that from antidiuretic hormone, for example. By keeping water in your body, you keep blood volume. Or by getting rid of water, you decrease the blood volume. And then I put there excretion of waste, obviously. So there's a cutaway of the kidney, a frontal or coronal cut of the kidney, and now we can see in there a little bit more. And let's look at a couple things in here. So the main functional part of the kidney, the main functional unit of the kidney is the nephron. So you see that yellow part up here? So I've got another slide where it's larger, but your kidney has a bunch of nephrons. This is like the smallest tube where that meets the blood. So this is going to be, that's the part of the kidney in particular that's going to be doing the filtering. And that nephron has actually kind of been enlarged in that photo. They're really small, and there's tons of them. But you get the idea. And if you follow this nephron, actually, if you can see it, there's like a little circle part right here at the tip of my pointer, and then there's these tubes. So there's like the circle part, that's where the blood's getting mixed in with it. And then there's these tubes, and if you follow these tubes, it goes from, this is still the nephron here. And it goes, and this right here, this long yellow part is called the collecting duct. So lots of nephrons are tapping into this connecting duct. So connecting duct, and then it goes into a minor calyx. So there's these are minor calyces. And then it goes into a major calyx. Where's the line between major and minor calyx? Who knows, right? So minor calyx, major calyx, renal pelvis, that's kind of this area here, and then out into the ureter. So that's kind of the order. They kind of put it here on the right. Nephron, collecting duct, papillary duct if you want to put it, minor calyx, major calyx, renal pelvis, ureter. It's kind of the order. And then some of these things, like these things here, look like pyramids. So they call them pyramids. That's just some anatomy, some orientation. There's columns here in between the pyramids, so they call those renal columns. So renal pyramids, renal columns, a little bit of fat. This region right here, they call it a hilus or a hilum. Is it marked anywhere? Oh yeah, right over here. So here they're calling it a hilus. Hilus, hilum, either word. And you have the same thing in other places in your body. Your spleen has a hilum, your lungs have a hilum or hilus. So it's not, that's just a general thing, like where you see how it like, how it dips in here, and here's where the blood vessels and the ureter are. So where it dips in there, that's what they call it. I just forgot to tell you before. Okay, so let me show me a better before we get to that. No. Huh. All right, I'm gonna go on the worldwide internet for 1 second. Show you a nephron. I don't know why I don't have a picture of one. Oh, Wikipedia. I hate when your teachers tell you, don't use Wikipedia. Why? Wikipedia is awesome. If I were writing a paper, I go to Wikipedia first. And then here's the trick. Go to Wikipedia and then scroll all the way to the bottom. And then get all those, do all those links. So ultimately, Wikipedia is not going to be in your references, but the references from that page will be in your references. This is a nephron. Obviously, it's not yellow here, but so there's actually 2 nephrons here. So here's one, and you see that there's like this round part, and they call this thing a glomerulus, and then there's tubes. This side of the tube's all convoluted, so they call it proximal convoluted tubule. And that's because proximal meaning that it's like close, right? If you think about your arm, right, proximal is your shoulder and distal is your fingertips, right? So there's a proximal convoluted tubule, and then it drops down here, loop of Henle, and then distal convoluted tubule right here. And then it goes into a collecting duct. And then here's another one here, same thing. Proximal convoluted tubule because it's closer to the glomerulus. I'll have that word on another slide. So proximal, loop of Henle, distal. You notice that when you look at both of these, this one has a shorter loop of Henle than this one. So most of the nephrons look like this. They've got the shorter one. We call those cortical nephrons. And then this one's called juxtamedullary nephrons. I think I got it on the slide. These nephrons they're for making more concentrated urine or more dilute urine. And then all these cortical ones are for making like regular urine. But anyway, these are 2 nephrons, so that's what they look like. Let me go back. And you can see that little one. You can see a little version of it up here, but it's not really a good one. Proximal convoluted tubule, loop of Henle, distal convoluted tubule, collecting duct. So this right here is the glomerulus. So this is where the blood meets the tube, right? So right here is the beginning of the convoluted tubule. So what's going to happen here is that we're going to create something called filtered fluid. Just a bunch of fluid from the blood is going to come out of here and enter here. And if you look at these blood vessels, there's like a bunch of slits in them. So they're a little bit different. Like they've got these different slits to allow different things to go through, right? You don't want to let everything out of your blood. Obviously, a first thing that you don't want to let out of your blood, you don't want to let the blood cells out, right? So you want to let the fluid out, but you don't, like the plasma and stuff, but you don't want to let blood cells out. And then there's other slits too, because you want to let some proteins out, but in general, you don't want to let out your plasma proteins either. So we want to get the garbage out, but we don't want to get the stuff we need in our blood out. Notice these cells here. These are microvilli. So they're absorbing things. I'm going to come back to this, but let me go here. So look, here's that round capsule, and here's the beginning of the tube. So let me go back. That's this. And then here's the beginning of the tube right there. So here it is here. So what I'm trying to tell you in this slide is that there is an exchange. There's fluid that ends up going into this glomerulus or this renal corpuscle. There's fluid that goes in here, right? And the fluid starts flowing through here, but that fluid's not like perfect urine because there's still some useful stuff in there. So what happens is that not all the waste makes it in here, and there's some good stuff that's in here still. So as it flows through these tubes, they're making exchanges, right? Reabsorption. So some stuff is going back in. Oh, I messed up. I actually need this. Get it back into the blood. Or later on, they're saying, oh, I don't need this. You take it, and putting that back into the tubule. So there's that initial, like, take all this crap I have in me, right? But then as it starts going through the tube, they start exchanging and, making it just urine. So there's three parts to this. We call this filtration. Same term. We called it filtration when we talked about fluid leaving a capillary. So this is the same thing, except that it's not going in an interstitial fluid, it's going into this tube. But we call it filtration. So you have filtration. Then you have reabsorption, just like with the blood, when we did the chapter on blood vessels. So filtration and reabsorption, you have the same idea here, except that we're talking about leaving a capillary and going into a tube. So there's filtration, there's fluid moving out, and then there's reabsorption, fluid moving back into the blood. And then you got a third thing, secretion. That just means moving back yet again. It's like a second filtration, if you could see it like that. So they're making exchanges as they go through. Here I'm kind of summarizing that. So glomerular filtration. You don't have to do that. It's up to you. What are you comfortable with? Both of us are. So glomerular filtration. So that was the first step, right? So all the stuff from the blood plasma, the water, and the solutes, they're going into that capsule. They're going through the capsule and then into the tubule, beginning of the tubule. Then some stuff starts getting reabsorbed, like the water, right? Because if I want to get the waste and stuff out, I'm moving a lot of water out of the blood capillary. I don't really want to move the water out, it's just that I have to because I'm getting other stuff out. I'm pushing other things out of the capillary. So water is going with it, right? But you need that water back. So here at reabsorption, most of that water is getting absorbed back into the blood. And then you have secretion. So as it goes further down this tube, you have waste, stuff like that, going into the filtered fluid. It's like another filtration. Whatever they weren't able to get out initially, maybe you can get it out in the secretion portion. And and we're not going to talk about any of this, but different parts of the kidney specialize in different things. So if we're going back to this one. So you have 3 parts of this tube, right? This tube is put into 3 sections. Proximal convoluted tubule, loop of Henle, and distal DCT. We just use the letters, right? Different parts specialize in different things. So, for example, here in the distal convoluted tubule, like there's medications that people take for high blood pressure, and we talked about like ACE inhibitors, and we talked about beta blockers that like slow your heart. But actually, the first thing that they're going to do for people with high blood pressure is they're going to give them a diuretic, right? There's different diuretics. Some of them are loop diuretics, so already you know what it's going to do. Loop diuretics affect reabsorption right here. It makes you reabsorb less water. But there's other diuretics that are called DCT diuretics, and so now you know those affect the cells here. Make those cells in the distal convoluted tubule, it makes them more absorptive, or it increases reabsorption there. And so a diuretic is all about making the kidneys remove more water than it normally would, or not. Let's say it a different way, not give back as much. Right, so you're, let me make it larger. So maybe a loop diuretic would make it, take back less water in reabsorption. It just depends on where it is, right? It's going to be the loop of Henle, well, anyway. So I'm not going to put that on the test. I'm just trying to make something relevant. Okay, pressure. This is definitely relative, because this is one of the things with high blood pressure. I mean, there's a few things. One, high blood pressure, it might loosen up some plaque or something, or whatever, and send it up to your brain and give you a stroke. So high blood pressure could cause you to stroke out. But another thing is that high blood pressure over a period of time is going to blow out your kidneys. Well, in particular, it's going to mess up your nephrons. So let's look at this, and this is talking about this. So there's a blood pressure. There's a blood pressure right here. A pressure just like there's a blood pressure in your arteries in your arm, there's pressure inside of your capillaries well, in your whole body, but your capillaries in your kidneys, they have a pressure to them, right? And then you have to overcome, this is a capsule, so you have to overcome this capsule. You have to get the water, the fluid past this capsule. So the first pressure, and you're gonna see that this is the same idea that we talked about with the blood. So you remember when we're talking about filtration and reabsorption in regular blood capillaries, we talked about hydrostatic pressure, right? And so same thing here. They just put the word glomerular, but really it's the same thing. It's blood hydrostatic pressure, just general pressure from the heart. That's the exact same thing that we talked about a few chapters ago. Then, if you remember, we talked about albumin. Is albumin in the blood or is albumin in the interstitial fluid? Here we're doing it a little bit different. The capsule prevents some of that pressure from going through. And then there's albumin in, not just albumin, but we're going to say albumin in the blood. So same name, blood colloid, osmotic pressure. Here, if you don't want to remember the word hydrostatic, even though it's right here, you can just put capsular pressure or the pressure from the capsule, right? So we've got three things. We've got a pressure, oh, look at that slide right there. Perfect. You got a pressure, your blood pressure, just your regular blood pressure, so that's the blood hydrostatic pressure. And then you have the capsule opposing that. And then you have albumin in here and other solutes. They're kind of pulling back on this. So if you look at it, they've done the math right here. 55 millimeters of mercury. Subtract 15 for the capsule. So the fact that you have to move across that capsule is going to subtract 15 millimeters of mercury, pressure. It's going to subtract from that. And then you subtract another 30 because there's solutes in here, and that's acting to kind of pull it back in. So when you subtract all of that, the net pressure of like this green arrow is 10. So good. Number 2 and number 3 are pretty much fixed. They're not going to change a lot, right? You subtract 15 millimeters of mercury because of the capsule. You subtract 30 because there's albumin in here. Those kind of stay. What changes is this. So if your blood pressure is like 120 over 80, then this number in here is probably going to be 55. And that's what this is saying here, right? Well, what if your blood pressure is, 140 over 100, right? This number is not going to be 55. It's going to be whatever, 70, making that up, but higher, right? And then that ultimately means that this number here, 10, that's going to go up a lot. Let's say that goes up to 20, right? So a small rise in your blood pressure, something that we would think is not like a big deal, but it's going to make a difference at the end here. It's going to, you can easily move that 10 millimeters of mercury to like 20. And so that's the issue. You don't want to put too much pressure in this tube. And after a while, it just, they don't work. So I would like you to know, I'm debating this. Okay, first of all, I'd like to know the function of the kidneys. So mark that as a note, function of kidneys. I don't care which ions, you don't have to memorize all of them. You should have, at this point, you should have an idea. If you see Na plus, you should automatically know that's sodium. You should know that K plus is potassium. And there's lots of ions. You should have an idea about some of the major ones. Sodium, potassium, calcium. That's a definite, right? We've been talking about that. Chlorine also. Those are standards. You're going to find that in any, not any, but you're going to find that in lab work. Anyway, you don't have to put it exactly like this. You know, if you don't want to memorize HCO, whatever, 3, negative, I don't even, like, you know, I can see it. When I see it, I know exactly that it's bicarbonate. But if you ask me to write it exactly, I might mess it up. I might put the 3 after the, I don't know. I was like y'all with chemistry, right? I took it, gotta be happy, that's it. Then I proceeded to forget everything. Because I was done with it. But you should be able to, at least if you see it, but sometimes they write it like this in like medical settings, then you know it's bicarbonate. Or more likely they'll just say bicarb. But anyway, function of kidneys. Probably not. Probably not going to ask you this. Because I don't know how to ask it. I mean, I really want you to know, just in your head, for you, that it's not just one filtration. It's not just water's leaving the blood and going into your P tube, and that's it. That is not at all it. The beauty of the kidneys is all in here, how things go back and forth in these tubules. So the story is not just about Act 1. Anyway, this, yes. Because it's, I don't know, I think it's pertinent. You have to know the pressures exactly. It would be nice if you knew what the pressure was here. Like as it goes into the glomerulus, you know, it's around 55. Or it would be nice if, I guess since we're doing numbers, and numbers I guess are easy. I don't know why. 10, you know, at the end, inside that tubule, we should have about 10, right? I'd like you to know what the pressures are, but, you know, I mean, numbers, I don't know, whatever. You're probably going to do the numbers because those don't look that difficult. But the pressures, you know, similar. You got a pressure from your heartbeat. If you don't remember this word, glomerular blood hydrostatic pressure, just write the part you know. There's the pressure from your heartbeat. Pressure generated by your ventricles. There's like regular blood pressure, however you want to say it. And then you could say, well, I don't remember capsular hydrostatic pressure. Fine, just say, oh, there's an opposing pressure because of the capsule. That's good. That's what it is. And then you can say, oh, there's solutes or there's albumin in the blood. That's also like an opposing pressure. So I mean, if you don't want to like write out the exact names, that's fine. As long as you know what it's doing. So I want you to know that. So what do we got? 2 questions? All right. And then that's really it. I mean, I really, you know, there is so much to that chapter on kidney. Right now I'm just going into electrolytes, but there's so much I feel bad that I didn't talk to you about it because you are going to have it. It's an important chapter. I probably should have taken out, I don't know what chapter to take out. I really don't know. Maybe immunity? I don't know. But anyway, doesn't matter. Here we are at the end. So electrolytes. I've written 3 of the big ones here. These are, I also wrote lab values. I'd like you to know, have a rough idea. Rough idea. So even one number, you don't have to know 136 to 148. You know, some labs don't agree with that number. Everyone has different ideas. This is a range. So when you look at ranges of things, you know, it doesn't mean that 149 is bad, or 135 is bad. That might be acceptable for Quest, but not for LabCorp or whatever. So you can say like 140 or something, you know, just this rough idea, right? So that you know, as you get further away from 140, then that might mean something, right? If your sodium concentration is like 110, you know, then you have hyponatremia. You don't have enough sodium in your blood. Maybe you're dehydrated. You know, someone that's dehydrated, and you look at the lab work and they've got hyponatremia, they've got a low sodium, that would probably explain it. Why is this person dumping out sodium? And this is a milliequivalents per liter, so that's what they use in these two. These what they call milliequivalent. I don't know what it is. I knew once. I just stopped caring because nobody cares, I think. But the numbers, right? And then chlorine or chloride, somewhere around 100. And then this is the big one here, potassium. And they're measuring that in something called millimoles, which again, you know, something to do with chemistry, a mole. Potassium's about 3.5 to 5. Potassium is, and I wrote it down here, I said hypokalemia, which is low potassium, is the most common electrolyte deficiency. There's lots of things that would cause it. Diuretics, for example, people that are on diuretics, they might have hypokalemia. Diuretics, steroids, people on laxatives. Maybe dietary, but more likely it's going to be something else, right? So if you see hypokalemia, then you would start asking those questions first. Are you taking any medications? That'd be the first place to go. Are they making themselves throw up something? I don't know. Were you sick? Did you have food poisoning or anything like that? But that's the most common one you're going to see. And hypokalemia or hyperkalemia, either way, is going to screw with your heart. So you remember the sodium rushing in and the potassium rushing out and the calcium trickling in, all that. Like that was important for the heartbeat, right? So out of those three minerals, potassium's probably like the most important contributor to this action potential. Like when you see the EKG and the lines go up and down and the P wave and QRS and all that, like if I had to choose one mineral, it'd be potassium. I think it's having the biggest influence on those lines going like up and down. So I'll just kind of leave it like that. Trying to make it simple. Kalemia meaning potassium, right? Because that one, it starts with a K, and potassium is K. And sodium is Na+, so NAT, so natremia. Same word, but with an NAT. Anyway, I want you to know the numbers. I'm usually not big into numbers, but you know, you could just give me a rough number. You could say like, if you you want it around 140 here. You can say if you want 100 here. This one, maybe you can be more specific on that one. It's a little more important to get that. Oh, look at that. That was my last slide. I didn't even get to tell you what they do. Well, okay, I'm not, so it'll be just like this on the test. You already have an idea of what they do, and I gave you, let's take sodium and potassium, the top one and the bottom one. You already know what they do. They're used in your heartbeat, right? They make the action potential. So they're important for any electrical thing going on in your body. So the ones from your brain, that is also these two. Sodium and potassium are going to be involved in like your nervous system, all the firing of your neurons, and then your heart. And then you know sodium has another job. It moves water around. Like diuretics, for example, make you get rid of sodium. So when you get rid of sodium, you get rid of water. I mean, you know the whole story, right? So you know that these, like you already have an idea. Chloride, we just talked about this. I mean, I didn't really say it directly, but chloride, we talked about it when we talked about the digestive system. I didn't say chloride, but I had it in another word. And it's hydrochloric acid. Now it goes back to chemistry. Chlorine, you notice it like chlorine when I had it written out on an earlier slide, it was Cl negative. Negative means that that's an electron stealer. The stealing's negative. It's not good to steal. Chlorine steals electrons. The one that steals is negative, and the one that gets stolen from is positive. That doesn't really make sense, but I mean, that's what it is, right? So hydrochloric acid, if you notice, I put HCl. H for hydrogen and then Cl for chlorine. Chlorine steals hydrogen's electron, then hydrogen is now H+. When something's a plus, it's a cation. Oh yeah, I'm using these words here. Cation means positively charged. Anion means negatively charged. All of these electrolytes, and I'm not going to talk to you about this on the test, but all of these electrolytes, they have places that they like to hang out, inside of a cell or outside of a cell. That's how we look at things in the body. We have an intracellular fluid and we have extracellular fluid. Intracellular fluid is in the cell. Extracellular fluid outside of the cell. Sodium is extracellular. It likes to hang out outside of cells. Potassium likes to be in cells. So you notice I put here main intracellular cation. Potassium likes to hang out inside of your cells. Sodium, I put extracellular. It likes to hang out outside of your cells. So you'll learn about that when you get more into renal physiology. You know, where these things like to hang out. So this is a really quick, not even an hour, quick introduction to the urinary system, and I just gave you a few electrolytes. I mean, they really deserve a chapter each. I know y'all not about to, you know, you just want to get out of here, and I don't blame you, because we're done. Now you just got to study for the final. And so, electrolytes, that's a question. That's a question. Electrolytes is a question. That's a question. And I said not that one. Then which one did I say? That's a question. So 3 questions. You're lucky. This is kind of a shitty chapter have to learn it anyway, so you kind of lucked out. And we didn't even do respiratory system. Reproductive system. So this one was like all right, I guess I'm talking about how important it was. Okay, does anyone have any questions? So I'm going to stop recording.
Yes.
Yes.
Dr. Klaus, I thought, so you gave us 4 questions on the last lecture on Monday. So you said 10 plus the 4. Now you said 3 more. So I'm confused.
So you have 3 from today and you have 4 from last lecture, right?
Right. And then
That's 7 questions from those 2 lectures, right?
right.
I'm going to pick 5 of those 7.
Okay. Okay.
So now you know every question is going to be on the final. I know that sounds a lot better than
No, we don't know every question.
you don't know the exact question. Like you don't know which ones I'm going to pick, but you know what they are. You have the test bank. I'll say that. Sorry, you have the test bank. You just got to spend some time with it. Let me stop recording.